Okay, it's again half duplex. Then I cannot hear if you are talking or if you have questions, but at least I assume you can hear me and you can see the slides. And okay, good morning. How are you doing today? Is today a good day for science or not? Hmm? Yes, you are right on. Morning. Morning. Bon dia. Okay. Then the fun part is over. Now we have to discuss about division, which, as I said many times, if I know how to do addition, I know how to do everything. But the question is how to do division faster. And this is, our goal for today. Here there are some slides. Okay. Some jokes by Farhani. Okay, then first of all, we have to understand the definition of division. Then you can see it as the inverse operation of multiplication, but this is true only when the remainder is 0. But in general, division stands for the fundamental theorem of the arithmetic. Some people do see it like that. And in mathematics, it is claimed to be like that. Then essentially, if you want to do division, you have two operands which are now not equal in width. You have the dividend, which is the one that you attack, and you have the divisor, which is the one which is active, which is doing the work. Okay, I can see also a student in 20. I hope you can hear me and you can see me. I cannot hear you, but this is kind of usual. Then the dividend is twice as large as the divisor. And this is obvious why, because if we think about multiplication, we had two operands for multiplication and the product was twice as large as number of bits. Now, I have these which are given, and now they are, unbalanced as bit width, and I am computing now two things. One is the quotient, and the other one is the remainder. Sometimes I don't care about remainder. Sometimes I don't care about quotient. If I want to do modulo arithmetic, I just care about the quotient, the remainder, because the quotient is not important. Now, I can compute the remainder directly, as it is the case here, but you will see later on that in other methods, you can compute the remainder later on. Come in, don't be shy. Not that you are shy. I didn't experience that in this university. Students are very, sure on what they want and what they don't want, right?
This is new to me.
It's new to you. That was my impression. Actually, it's good to know what you want and to manage your time in a proper way at least. Okay, now then I have to do these two jobs. And now if you look at the representation, the dot representation, it looks familiar to you, right? It's different, but it's familiar. And you would say, because I have those dots, I'm doing here some subtraction, I should be able to do it in parallel. But this is not true. Because while in multiplication, I knew the partial matrix at the beginning, I could generate it. In the first step of the multiplication, in here, I have a serial inherent process. Then I cannot say, okay, I have these dots, I'll subtract from this all these numbers, and this is my result, and I'm done. Somebody shine, or maybe wrong door. Then, what I am doing, I am trying to converge to the solution. Then division is by definition a convergency process. And I'm starting with an approximation of the quotient from the most significant digit of the quotient, and I'm getting down until the least significant digit, one at a time. Then I am trying to see how many times I can subtract the divisor from this value, because this will give me the quotient. And you remember how you did it in primary school, right? And what you are doing, you are trying to guess, let's say what I have, 93 divided by 13. You are trying to guess a quotient digit, which was good, right? Now, this guess is not a simple matter. In here, it's simple because it's not 3. Make it 99 to make it simple. Okay, then, what? I'm not awake, huh? This is what I wanted to say. 39 divided by 13 will give me 3. And I'm in business. Now, if this is not the case, this guess, it's an iterative process. First of all, I have to make here a right guess. If I am going for a 2, I'm not doing the reduction good enough. Then this will be too large. If I'm going for a 4, this will become a negative. I'm too optimistic. Then the first challenge in division is to make the right guess for the quotient digit in the current position. If I do that in decimal, I have a very wide choice. I can choose between 0 and 9. Luckily, we do business in binary. Then my choice, it's even 0 or 1, which makes my life easier. Now, due to the nature of the division, the remainder has to have the same sign as the dividend. Sometimes you allow for a negative remainder, but this is it's not according to the fundamental theorem of arithmetic. Then when you do this process of division, you are trying to diminish z, which is your dividend, towards a value which is smaller than the divisor, because if the remainder is not smaller than the divisor, you are not yet done with the division. You can still increase the quotient, and you are doing that while preserving the sign or the relation between the sign, good morning, the relation between the sign of the dividend and the remainder. Then essentially speaking, what you do is something that you know, but now it's very sequential. You start with you make the first guess, and this is the most significant digit of the quotient. And you multiply it with d, and then if this is decimal, it's complicated because I have to find this value which is the most appropriate one. But if this is binary, this is even doing nothing or making a subtraction. Now I'm making that subtraction, and hopefully my guess was good. Let's say 1 was okay. The result, it's still positive, which means I didn't overdo it. And then I go to the next one and to the next one, and I have 4 steps. Because the definition of my division is in such a way that I have, in this case, 8-bit dividend, 4-bit divisor, and I should produce a 4-bit quotient and a 4-bit remainder. However, I may have an overflow here. If the proportion between the dividend and the divisor is not okay, 4 bits might not be enough. Let's say I'm dividing z by 2, just to make it simple. The value will require 7 bits. There is no way to push that value in 4 bits. Then one condition that I have to check before I start the division is the overflow condition. And I will have an overflow whenever this part, the most significant part of z, is larger than d. But there is something else peculiar in division, right? What is peculiar in division? I cannot divide by 0. Then I also have to check before doing the division whether or not d is 0. then I will not proceed with the calculation before I do those checks. And when I'm doing those checks, I can go further and do the calculation. Now, what you see is that I have an iterative process. It will take me k cycles to complete the division. When, you know, I have the problem defined in this way, and in this case it's 4 cycles. I may have to spend the cycle in doing checking for overflow, for division by 0. Then, roughly speaking, I can do it with 4 cycles, 4 or 5 cycles. I cannot do more than one operation at a time because they depend on each other. The choice for Q2 will depend on choice of Q3. I already know, because you know I'm an expert in arithmetic, that I know that high radix may help me. And what we know, or you should know, whenever you attack a problem, it was not supposed to happen. Maybe I'm talking too much and I'm not moving the slides, right? Then whenever you attack a problem in arithmetic, you know by now that you have 2 approaches, high radix and carry save errors. Carry is the problem. And if I have the opportunity, I will rely on a different kind of representation of numbers. Then I go for RMS, for sign digit, whatever redundancy. I can also try to do this process in a different way. I can try to subtract from Z D a number of times in an iterative way. Because what I want to know is how many times I can subtract the divisor from the dividend. That will give me the quotient. And then I can do now divisions, the division in a very ineffective way, which will be, I will start and do subtraction, and I'll subtract first D. If the result is positive, I'll say Q is 1. I try it again. If the result is still positive, Q will be the previous Q plus 1. And with each and every subtraction, I'm increasing the value of Q. Whenever I get a negative result, it means that I already have the solution. Now, this approach is not something that we do, because the number of iteration will depend on the value of Q. Then assuming that I have, like here, 4 bit, and that Q is 7, I would have to do 7 subtractions. Actually 8, and on the 8th one I stop. This is another way to treat division, but we are not doing that. We are doing it in a different way. We are targeting the reduction from the top. Then I'm trying to guess the value of this guy, because this guy, it's actually the one that will take the most from this Q, because this guy has a weight of 2 to the power of 3. Yes, you are with me, you know. Then that's the reason why also in school, when we do, you know, pen and paper division, which most likely you don't do today, do you? No. Where is the pocket calculator? Do you have one? You know, your smartphone can do that, right? By the way, at the exam, no smartphones. The pocket calculator, it's okay, but you know, smartphones, they have a kind of strange property. They have webs. And okay. Now, in here there are some latencies for Pentium 3. Those Pentium 3, those are all kind of things. But essentially, what we can see from here is that while we can do good work from addition and multiplication, okay, when we deal with division, this is very slow. And the reason why it's slow is because of the nature of the division that I was just explaining. Now, there is here an update from 2012, but things are scaling with the same kind of tendency. Then, how do I do the division? Then I'm doing in radix 2, and I'm starting now from the most significant digit of the quotient, which is the one that I guess. And I have an iteration, which is, you know, I have to align things in such a way that I'm doing the subtraction in a proper way. Then I have to shift, and I will assume that I am processing what is called the partial remainder, which is the value that I'm generating as an approximation of the final remainder. My first approximation for the partial remainder, it's actually z. It's the value that I am working on. And slowly but surely, I will subtract from this each and every iteration values, which are determined by the position of where I work, and 0 or 1, depending on if that is possible. Then you see, my iteration is kind of simple. I'm doing a shift and a subtract. And because this is binary, I even subtract something that I know, or I waste my time. If I go for higher radix, in here things will get complicated. Now, I can do that on integers, or I can do that on fractional numbers. It will be the same. The only difference is that I will see a 2 to the power minus k because I have the decimal point, which is only in my mind. It's not represented in hardware. Then, I will have to check about the overflow condition, because why would I waste my time to try to do the division when the result will be useless anyway? Then the first cycle of the calculation will be to do that check. And in order to do that check, I have to compare the most significant part of Z and D, which is I have to look at these 4 bits of D and of Z and compare them with D. If this is larger than this, I should stop because I will not be able to represent it on 4 bits as it is my case. Now, you already think maybe that this looks a bit like the multiplier, right? Because it's the same kind of process. And here we have some examples on how this is done. Okay? Then, and you have also with numbers, you start with Z, and then you have D. You see, you multiply it with 2 to the power 4 in order to start the subtraction from the right position. But this is not a multiplication, neither a real shift. It's just the right wiring of the operand to the other. Okay? And then in this example, you just have calculations which are done not like in a computer. Then I am just saying, you see, this is my initial reminder, I'm doing a shift. You see, I already did a padding here. I put a 0, which in this case is not real a sign extension. But when I will do it for sign numbers, I have to do sign extension. Now, I make a shift, and then I am guessing that the first quotient digit is 1. Why am I guessing that? I am guessing that by visual inspection. I will look at this part of shifted partial remainder, and I would look at D, and I can see that this is larger than this, which means when I will do the subtraction, I will get a positive result. Then a guess of a 1, it's okay. Then I'm doing the subtraction. 0, 0, 0, 1, 1, 1 minus 1 is 0. Okay, 1, 1 minus 1, 0. And this is my next partial remainder. I made the first step towards the partial remainder, and I remember that the quotient, the first quotient digit is 1. Remember, this is now the most significant one, not the least significant one. I apply the same. I'm doing now a shift. And now I see, if I'm trying to subtract 1010 from this, I'll get a negative number. Then my right guess will be a 0. I'm just wasting a cycle, and then I go to the next. Then I am reporting 2s in here. I do another shift, and I look again. Now I have 5 bits which are active, then by no means, given that this is 1, I'll get a negative result. Then I can guess for a 1. This is my result. Again, this is a subtraction. This is not done in 2's complement. It's just for us to understand how it works. And then my final calculation is this, where I guess a 1, and this is now my remainder, and this is the quotient. Okay? The quotient is, I have it directly in binary. It was 1011, which is 11. And then the remainder, you see it is aligned here as it would have been multiplied with 2 to the power 4. But actually it should be here, because the remainder cannot be multiplied with 2 to the power 4. If it is, then my entire calculation is not correct. Remainder has to be smaller than d. Then you already see that in the iteration, my problem will be to make the guess for the quotient, do a shift and an addition. The same holds true here for fractional. It's no difference. What you see is that if I do fractional stuff, when I finish the calculation, you know, the fractional quotient is the same, but for the fractional remainder, I will have to shift it 4 positions to the right. And now, this will be a real representation which will count. Okay? Now, I will not store all these bits. I will just remember this, but I have to know that it's out of the domain. That somehow the decimal point is not here, but here. Because if I put the decimal point here, I didn't do the right thing. Okay.
Excuse me.
Yes.
Could you repeat how did you guess the second quotient?
Which one? Here?
Quotient 2?
This one?
Yeah.
Okay, this is my new partial remainder. I can try to subtract d. And my d is 1010. If I subtract 1010 from this 1001, I'll get a negative number because this is larger than this. And if I get a negative remainder, it means that I'm infringing the rule. My rule is always to preserve the sign of the remainder the same as the sign of z. Then when I get a negative result, I am refraining myself. If I can subtract and still get a positive result, I stay in business. It's the same when you do subtraction or when you do division with pen and paper. And you say 4. If I can guess that the digit here is 4, I'll say 4 times 3, blah, blah. It's larger than 39, then it will give me negative, then 4 is too large. I'll try with 3. When you do it with pen and paper, this is what you actually do. You don't reason slowly each and everything like that, but you see, you look at this and you look at that, you have some experience, you have some feeling, and you say, my guess will be probably a 6. You might be wrong, around, not in this case, that's a wrong guess. But in a computer, you have to do it in a fast and informed way. And in binary, essentially, in order to make that choice, you have to make a comparison. If you want to make the choice and then do the addition. But instead of the comparison, it's actually a subtraction or an addition. Then you will do it anyway, and depending on the result, you will commit it or not. That's basically the way you do the division. Now, the same story with history, when we had no blah, 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 we were actually using this methodology to do, you know, division in assembly program and also microprogram. It's exactly the same old story that we discuss about. This is not interesting any longer because we now have real machines. Now, this is the way we build it in hardware, which looks to you very much familiar. It looks like a serial multiplier, but it's not really a serial multiplier. The main ingredients are the same. Now, what I have is, I have a register where I put Z, and a register where I start to store Q. And I'm guessing Q one at a time, based on what? I am looking at the, okay. Let's look first on the mechanism, and then I will tell you how I make the calculation of the quantity. Then practically what I'm doing is I'm taking the partial remainder, which is initially Z, and I'm doing always a subtraction of D. This in here doesn't really make sense now. It's useless because I'm always subtracting. But the reason why it's here is because I might want also to add, as you'll see later on, and I also might want to use this for multiplication with different kind of setup, but the same hardware. Then, I take the partial remainder, I always subtract D, and I get a result. Now, this result, I'll put it back in this register with a condition that is determined by the value of the quotient that I am obtaining. If this result is positive, this value will be 1, and then I am loading the trial difference, and I'm also injecting a 1 in the quotient register. Now, how do I know that this result is positive? This result is positive whenever this is positive, okay, and this is, I can tell that by looking at the carry out of this adder. Now, you should not assume that this holds true in general. That not always when I'm doing 2's complement operations, carry out is telling me something about the sign of the result. In this case, because I'm always doing, I have a positive value and I'm subtracting a value from it, then I add a positive with a negative value. Always carry out means that result is positive. And remember something, I didn't say anything about the sign. Then so far, we just work with unsigned numbers. Okay? Then I will have a good result whenever this is positive, right? And then, you know, when I have this bit 1, because when this bit is 1, for sure, this will be fine. Okay? Then with a simple OR gate, I will generate the quotient. This is called restoring division. Then I said I could do a comparison, then decide on the quotient, and then do the subtraction. But this will cost me 2 additions. What I can do is in here, I am trying to make my best guess, my optimist guess, which will say Q is 1. Let's do the subtraction. If the result is positive, my guess was good. And I can update the partial remainder, the trial difference can come inside, and the quotient can be updated with 1. If this is not good, then the result is a negative number, then this gate will produce a 0, which means being a 0, the trial result will not be stored in here. This will not be stored, and I will inject a 0 in here. Then in k cycles, I'm done with the calculation. Okay, here we have an example of unsigned division, restoring unsigned division. And now it is as it would have done in hardware. Then first of all, I check the overflow. Okay, you see there that the first 4 bits of Z are not larger than D. Then I'm sure I can commit the division. And now I'm stuck doing things. I always do subtraction. Then this is D and this is minus D. Now we deal into complement numbers. Then this is the complement of that plus 1. Then I shift, I do the subtraction. This is my result. As you see, the result is positive. Then I can set Q3 for 1. I can update the trial difference. I can shift and I can try again. Now this will give me a negative number. Okay, this is the result, which now is negative. Then because this is negative, my guess was wrong and I should go for a 0. But while I'm going for a 0, I'm not storing this negative result. I'm just restoring this. Then my previous partial reminder, it's actually the one that I will work further. And then I am restoring, I obtain this. I still do a shift because now I move to the next position and I try it again. And I'm doing now again a subtraction, and then I have a positive one, then I put a 1, again I do a shift, I'm doing again a subtraction, and I have 1. Now this is the way things will work in a hardware, in a piece of hardware. Then what you see is that I have to pre-compute minus D, but this is not required because I have that max with the inverters or with the XOR gates. And what I am doing is I'm always doing a subtraction, then each and every cycle I'm doing an addition, and then I'm checking the result of the addition. When positive, I report a 1, update the result. When negative, I report a 0, and I shift the previous for the next iteration. Okay. Now, division can be handled, when, we always start with unsigned numbers in order to clarify the basic mechanism, and then we go into signed numbers because those are the relevant ones. And for division, there are different ways to deal with the sign. There is a relation between the sign of the operands and the sign of the quotient and the sign of the reminder. You see, if both of them are positive, both of them are positive too. If the divisor is negative, the quotient is negative, but the reminder is still positive. Then we don't get this. This is based on the rule that the reminder and the dividend, they should have the same sign. In here, you see, it's negative, negative. Now, I can deal with that issue on a different pipe than the calculation of the magnitude. Then I have signed numbers. I can make them positive, do whatever we did in the previous slide, and then correct for the sign according to the rules. Then sign of S and sign of Z should be the same, and this is the condition which will give me, the fact that I'm doing okay, I'm doing the right calculation. Then this has to be smaller than D. Otherwise, I didn't do the convergence until the end. This is one way to do it, and this is part of the paradigm that we discuss in the very, very beginning of the course, when I said that you can deal with sign in a direct way or an indirect way. In here, this is an indirect way which can help. However, you most of the time want to deal with this in a in a direct way, but before going there, as you will see when we talk about division, we'll make a lot of detours until we arrive to a solution which is okay. Now, before going there, let us look a bit on the cycle time of the non-restoring division. Gesundheit. Then, in a non-restoring division, I am doing a couple of things in the cycle. Then I'm doing this subtraction, then I check if the result should be updated, and then I will do the update. Now the question is, can I get rid of that? Can I always store the result? Because this will make my life a bit less complicated. Then try to store the result also when you get a negative intermediate partial reminder and correct later on. Then I have to be able to correct later on, because otherwise I'm going in the wrong direction. Then in the next iteration I should do something else to still get the right value. Then the principle behind this approach is to say, I will do now a wrong calculation, but I will fix it in the next cycle. This will give me a simplification in each iteration, because now, regardless of what's going on in here, I will always store. Then I don't have to think first whether or not I'm storing. And this has a simple justification. Then, if I am doing a subtraction, which gives me a negative result, this is the previous partial reminder, and this is what I subtracted in this iteration. This is negative. What I can do is, I can do restore, then take again this, shift it, and do this calculation. Or I can say, okay, I'll keep it, I will shift it, and now instead of subtracting, I will add. And this will give me this result. Then what I see is that there are two roads which will bring me to the same result. I am allowing to infringe the rule which will say that Z and S should have the same sign, but only for one iteration, and I will correct that later on. And you see, this represents what's going on. Then I made the first guess here, 1. It was a positive, I did a subtraction, and now I get a negative result. For this negative result, now what I will do is I will use it, I will shift it. I will not subtract, you see, I'm just adding now, and I report the 0, and then I continue. From the hardware point of view, this is a very good simplification. It costs me nothing, it saves me some time, and is not bringing me towards the wrong result, which is the first and the most important condition. And you can check that I get the same beautiful number. Now, this is a diagram which is giving you a representation of the evolution of the partial reminder. Sorry. In the two situations, restoring and non-restoring. And what you see is that in this case, you know, I start with it, I'm shifting, I subtract, I shift, I subtract, this is wrong, I don't like it, I restore, I shift, I subtract whatever, and I arrive to this, which is my right result. And in non-restoring, the only difference is that whenever I get here to a negative, I keep it, I shift it, and now add. Then, in other words, I can see the convergence process going in different ways. then when I am doing non-restoring, I allow for some spikes to overshoot in the top of the value that I'm looking for. While when I'm doing restoring, I'm always converging from under the value of the target quotient. Now, is this important the way I converge? In this case, not. If this would have been a digital filter, the fact that I overshoot would not be good, right? Then this is not the result of a filter in this kind of strange reaction here. This is just the trajectory that I'm following from my first guess towards the final calculation of Q. So far, so good? Okay. Some of you are very tired or bored. I see you.
I'm sorry. So, can I ask a question?
Yes, you.
Is it possible that the overshoot could shoot up so much to
No.
the point that...
No, it's not possible because this is a convergency process where you always keep things within bounds. Then by doing this, let's say you accept for one iteration to go wrong. If you would accept for two iterations to go wrong, then you are too far away and most likely you cannot return. But the principle is that I am doing now, I allow myself now to make a wrong choice, but I will correct it later on. And this is possible also in other cases, as you will see in division. Important is to reach the target. If you deviate from the road a bit and you correct, that's not a problem. Now, there is a way, you know, we look in non-restoring division because we wanted to simplify the hardware. But there is an extra aspect which non-restoring division is bringing you. You can try to do sign division in this way with a simple rule that will drive the operations. Then in non-restoring division, what you are doing is you are choosing for addition or subtraction depending on the value that you obtain, which was supposed to be positive. Now let us assume I have unsigned numbers. Now let us assume that I have signed numbers. Now I will use the same alternance between adding or subtracting, but my rule will be different. What I will try to do, I will make a guess on the quotient by comparing the sign of S and the sign of D. Then while I'm doing the division, I am trying to make those equals. If the sign of D, which is the divisor, and the sign of S, which is the partial remainder, are the same, I will choose a 1 and I will do a subtraction. If they are not the same, I will choose a -1 and I will do an addition. Then I will always do an addition or a subtraction. My checking for the direction is simple. I just compare two bits. I only have one problem because now I have 1 and -1, which are not 1 and 0, and I have to deal with them. Now, do you remember kind of booth recoding when we are trying to replace a string of ones with a negative number and then a 1 somewhere later on? Here it's somehow different. Then while in the non-restoring case, I can be too optimistic here and I will have to correct a number of times to get the same value. This will simplify the choice and will give me this extra capability of dealing with the sign in the direct way. There is one thing which I did not mention and is very important, that while I'm using this to drive the entire process, After I finish my calculation, I may end up with the sign of the remainder, which is not good. Then I will need an extra cycle at the end in order to correct if the sign is not good. Then if z is positive and my remainder is negative, I have to make my remainder positive. Or if z is negative and my remainder is positive, I have to make my remainder negative. Then what I have in this situation is I'm dealing with signed division in k plus 1 cycles. The plus 1 may or may not be there. But there is no, I'm not, actually I'm unaware about the signs. The fact that I'm dealing with signed numbers is transparent. I don't care. I just look and try to, you know, to equalize the signs of those guys, which for me are just 2 bits. If they are the same, I make a choice. If they are not the same, I make another choice. But at the end of the calculation, I have to make this check, and then to see if z and the remainder do have the same sign, and if not, I have to do a compensation iteration. Then okay, you also have to take a break. I'm pretty sure you know.